All right. Good morning, everyone. So today we shall continue our discussion uh, on LR1 parsing from the last class. In the last class, we have seen uh, how to construct the LR1 automaton. I will briefly recap the intuition behind the construction of LR1 automaton and build upon that intuition further in today's session. So if you see in this LR1 automaton, you start from state I0, which is the initial state, and the kernel item in state I0 is S prime goes to dot S followed by dollar. This is the kernel item. What that kernel item means is that we are anticipating an input string which is derivable from the start symbol S followed by dollar. So that is what uh, the meaning of that kernel item in state I0. And then we apply closure function on that kernel item and we get all these, the rest of the LR1 items. And now when we are in state 0 and when we see ID as an input, so then what happens is we move the dot over ID. If you see, so this is one LR1 item with dot before ID, and this is another LR1 item with dot before ID. We move the dot before over the ID, and we come to state I5. That means we have seen is the input symbol ID from the input stream, and we are shifting it onto the stack and or someplace, and we are going to state I5. And when we are in state I5, what it means is we have seen a string, we have seen ID, and we are anticipating equal to or dollar from the inputs, from the input string. Similarly, if you see this example, I0, when we are in state I0 and when we see a string derivable from L, from the non-terminal symbol L from the input, then we go to state I2. And when we are in state I2, what it means is, if you look at this kernel item, this particular kernel item, what it says is we have seen a string that is derivable from L, and we are anticipating a string that is derivable from equal to R from the rest of the input that is not consumed. Or the second LR1 item says that we are just anticipating a dollar end of file symbol from the input. So like this, we start from state I0 and we keep expanding this LR1 automaton. At some point, the LR1 automaton gets closed. That means we will not be able to generate any more new states. So once this LR1 automaton is constructed, so we construct what is called as an LR1 parsing table. So this LR1 parsing table, so if you see the rows of the LR1 parsing table, they are labeled with different states. So if you see, there are 13 states in this LR1 automaton, and so each row of this LR1 parsing table is labeled with these states. And then it has the columns can be partitioned into two. So one set of columns, they correspond to what is called as an action part. And the second set of columns, they correspond to what is called as a go-to part. And if you see the column labels in the action part, they correspond to terminal symbols like star, equal to, ID, dollar. These are all terminal symbols in the language. And then we have and the go-to part, the columns in the go-to part, they are labeled with non-terminal symbols, capital S, capital R, capital L, and capital R, right? So let's see how this parsing table construction happens. So when we are in state 0, when we are in state 0 and when we see a star, what this entry says is shift star onto the stack. You will see that in order to do the parsing, we use a stack because we are constructing a deterministic push-down automaton. So we need to use the stack along with the input table. So when we are in state 0 and when we see star, what the action that we have to do is we have to shift star into the stack and go to state 4. That's what we are doing here. State 0, and when we see star, you shift star into the stack and go to state 4. And when we are in state 0 and when we see an equal to symbol, there is no entry here. This is a parsing error. This is not supposed to happen. When we are in state 0 and when we see equal to symbol, then that's a parsing error. And you can immediately see that this in some sense satisfies the viable prefix property. So we talked about this viable prefix property. So you know that there is no string in this language which starts with equal to symbol. So the first symbol turns out to be in the input string W. Let's say the input string is something like, this equal to is the equal to of the input terminal symbol followed by ID, but there is no string which starts with equal to, so immediately it reports an error. Similarly, when we are in state 0 and when we see an ID, we shift ID into the stack and go to state 5, and that is what is encoded here. And when we are in state 0 and when we see a dollar, there is no parsing action available here, then that means it's a parsing error again. And when we are in state 1 and when we see a dollar symbol, then that means we say it's accept. So we have seen a string that is derivable from S, and we have seen the end of file symbol. So we accept the input string. Let's look at state 2. State 2 is interesting. So when we are in state 2 and when we see an equal to symbol, then we shift equal to onto the stack and go to state 6. That's what S6 means. Shift the symbol equal to on the stack and go to state 6. Again, when we are in state 2 and when we see the dollar symbol, then what it means is apply a reduction. So that is, what is the reduction that you want to apply? Replace L that is present on the stack with R. And we want to apply the reduction R6. What does this 6 refers to? This 6 refers to the substitution rule, R goes to L. So when we are in state 2 and when we see the dollar symbol as the next input, as a look ahead symbol, we want to apply a reduction. And what reduction we would like to apply? It is given by the substitution rule number, which is 6, which is nothing but R goes to L. R goes to L. So like this, we will build the whole of the action part of the parsing table. And then we have the go-to part of the parsing table. So when we are in state 0 and when we see a string that is derivable from S, then we go to state 1 and that's what we have. So this is the go-to part. State 0, you have seen a string derivable from non-terminal symbol S, then go to state 1. You are in state 0, you have seen a string that is derivable from the non-terminal symbol L. Now you go to state 2. And you are in a state 0 and you have seen a string derivable from the non-terminal symbol R. Then you go to state 3. And when we are in state 1 and when we so when we are in state 1, this is not a possibility. Like there are no outgoing transitions from state 1. So there are no entries associated with the go-to part here for associated with the state 1. So like this, we take the LR1 automaton and construct this LR1 parsing table. So now let's see how we can use this LR1 parsing table to do the parsing. And through this example, you will get more intuition. So you are in state 0. So the way the parsing starts is the parser starts in state 0. So you have the parser, it has a stack and it has the input tape. On the stack, the state 0 is present. So what happens is when when the top of the stack is state 0, and when it sees ID, and if you go and check this parsing table, what it says is shift uh, ID onto the stack. So you shift ID onto the stack and you put 5 also here. So actually you don't need to store this in between thing ID. In order to shift ID onto the stack, you just have to shift state 5 onto the stack. Because when you see the label of the transition going from state 0 to state 5 is ID, by shifting state 5 onto the stack, you are implicitly shifting the terminal symbol ID onto the stack. But we are still writing it here so that you understand what is there on the stack. Okay, so understand what is there on the stack. So now we are in state 5, and the next input symbol is equal to. So you go look at this parsing table. So this is the thing, state 5 equal to. So this is the action. You have to apply a reduction using the substitution rule L goes to ID. How do we apply the reduction? So you pop ID out from the stack. So while popping ID out, so you essentially pop ID and state 5 out from the stack, and you push L onto the stack. So you push L onto the stack. So what happens is when you pop ID out from the stack, what gets exposed is you kind of retract back in the LR1 automaton by one state, and you go to state 0 because that's what is there here. And when you are in state 0 and when you see a string that is derivable from L, you go to state 2. And this is what we end up. So these two steps are important, and we keep applying these steps again and again. So here we applied a shift action in order to move from this configuration to this configuration. We applied a shift action, and in order to move from this configuration to this configuration, we applied reduction action. And then when we are in state 2 and when we see an equal to symbol, what happens is you shift equal to onto the stack and go to state 6, and that's what we are doing here. We are shifting equal to onto the stack and going to state 6. And when we are in state 6 and when we see the next input symbol star, what we do here is this is what is happening. So we shift star into the stack and go to state 11. You go to state 11. So this is the current configuration. And when we are in state 11 and when we see ID, so here we are in, and when we see ID, you go to state, you shift ID onto the stack and go to state 2. So you shift ID onto the stack and go to state 12. And when we are in state 12 and when we see dollar, then what we have to do is we have to apply a reduction operation. That is, we have to pop ID out from the stack and push L onto the stack. So when we pop ID out from the stack, what gets exposed is because you have reached the state 12 along this path. Remember, you can reach state 12 in two different paths. But we have reached the state 12 along this path. So when you pop ID out from the stack, what remains on the top of the stack is state 11. And when we push L onto the stack, then what happens is you go to state 10. And that's what happens. You pop ID out from the stack and you push L onto the stack. And pushing L onto the stack is equivalent to going to state 10. So now we are in state 10. And when we see dollar, then again, what happens is we want to apply a reduction. What is the reduction that you want to apply? We want to pop L out from the stack and we want to push R into the stack. Popping L out from the stack is equivalent to coming back to the state 11 via which we approach this state, and pushing R is equivalent to going to state 30. So you pop L out from the stack, state 11 gets exposed, and you push R into the stack, you go to state 30. And when we are in state 13, and when we see dollar as the next symbol, then we want to apply a reduction operation. That is, we want to pop star and R out from the stack. When you pop star and R out from the stack, what gets exposed is state 6, because remember we have approached this through this state, through this intermediate state, and it gets exposed here. You pop all this out, and then you push, you replace star R with the non-terminal symbol L. You push L onto the stack, and so we are in state 6, and when we push L onto the stack, you go to state 10, and that's what happens. So now we are in state 10, and dollar is the next input symbol, and what's the next action? So let's see. So it is not here. Let me try to see if I can draw. Yeah. So let me try to draw here itself. When we are in state 10, and when we see dollar, we would like to apply the reduction operation. L goes to R. So what we do is this is 0, L, 2, yeah. So when we pop state 10, we are in state 10, and we want to pop L and we want to push R. 6. When we are in state 6, and when we push R, you go to state 9. So this is dollar. So sorry, my handwriting is not quite good here. This is L. Let me rewrite. Or I will open an editor. Yeah, so what's the big deal? I'll write here maybe using a different pen for contrast. Yeah, let me write here. Yeah, so here the configuration right now it is 0, L, 2 equal to 6, L, 10. This is the state in which the stack, this is the configuration of the stack, and dollar is the input. Dollar is the input. I'm putting a line separating them. And when we are in state 10, when we are in state 10, and when we see dollar as the input, then we have to apply the reduction. That is, we have to pop L out and we have to push R in. So popping L out, we go back here to state 6, and pushing R, we go to state 9. And that's what we do here. 0, L2 equal to 6, R, 9. And when we are in state 9, and when we see dollar, then again we won't apply a reduction operation. So we pop L equal to R from the stack. And so popping L equal to R from the stack, so what happens is we go back state 0, which is there on the stack, gets exposed. So you go to state 0 because you are popping out all this and you are pushing S onto the stack. When we are in state 0 and when we see S, you go to state 1. And when we are in state 1 and when we see dollar, then you can see that it is an accept. That is, we have seen a string that is derivable from S, and so this is what is called as an accepting configuration. This is an accepting configuration of the pushdown automata. So we have seen a string that is derivable from S, and the next input symbol is end of file symbol. So we are all done. So this is how we can parse an LR1 parser, parses an input string via a sequence of shift reduce actions. So via a sequence of shift reduce actions, if it can reach this accepting configuration, then the input string W is a valid string described by the grammar. And if it is not able to reach this accepting configuration because it has hit an entry such as this or this or this, then it emits an error. It emits a parsing error. And one interesting idea that I would like you to make a note here is if you join what is present on the stack and what is present in the input, this configuration and this configuration together, let me change the color, then you get the rightmost derivation in the reverse. So you can see, yes, this is nothing but if you have to do a derivation, let me, yeah. So if you have to do a derivation, maybe you will start rightmost derivation, you do S goes to L equal to R, and you can see L equal to R here. And then in the leftmost derivation, we replace the leftmost symbol, you replace this R with L, so you get L equal to R, this is what you have. And then you replace this L equal to this L with maybe star R by applying the substitution rule 4 here. So L equal to uh, star R, and you can see again L equal to star R is present here. I'm continuing the derivation process here, and then you can replace this uh, R with L. So we can have L equal to star L. So this corresponds to this stack state. And and then you can replace this L with ID. So you get L equal to star ID. And you can see that L equal to star ID, this is the current configuration. And then what happens is you replace this this L with ID, you get ID star. So what you can notice here is and this one L equal to star ID, it corresponds to this particular stack parsing machine configuration, parser configuration. So as what I would like you to notice is if you look at the stack and the input, and by looking at the state in which the stack and the input has progressed as a parsing process kept going on, you can construct the rightmost derivation of the input string in the reverse order. So we are constructing the rightmost derivation of the input string in the reverse order. So if you see here, from here you can go and then we continue here, and then no, you keep going here, and so finally we can construct the rightmost derivation of the input string in the reverse order. So this is the important observation I would like you to make. I'll take a pause here and see if you have any questions. You're all good? Are you all with me here so far? So if you're doing good, can you say yes on the chat so that all right, I see at least there are some students who are with me. Thank you. So, it's important for me to know that you are with me so that I'll get some energy to keep moving forward. Let's So this is so one interesting thing I want to say. So usually when I teach this in a physical class, I used to have a great problem because this LR1 automaton, drawing it on the board is a pain. So if I put this on the slides, then showing this LR1 parsing automaton, this parsing table, it is manageable to draw it on a board, but still, I don't want to draw this big table on the board. So showing both these things together on the screen used to be a problem. Now with all this virtual stuff, I'm able to share whole of my desktop, and that way you are able to see all the three important things. One is LR1 automaton and how the LR1 parsing table is derived from the LR1 automaton, and third, how the LR1 parsing process happens. Right? So now I don't need all this now, so I will just close this. Just give me a minute. I'm just setting things up for you. All right. Are you able to see the screen now? Great. So now again, coming to our idea of parser generators. So if you think of an LR1 parser, the interesting thing is, so it has a stack using which it stores some context, and it has the input tape. And then this is the core algorithm. And then there is this parsing table. This is the parsing table. What changes from one grammar to another grammar is this parsing table. The rest of the stuff remains the same. So given a grammar, if you can generate the parsing table, then we have then we have the parser ready. And that is how parser generators work. So the parser generators like Bison, uh, so what they do is they take some grammar file, let's say grammar.y, and then they kind of generate the parser. And the way that they generate the parser is the core parsing algorithm remains the same, but what they generate is primarily the parsing table. As someone noticed from the last class, this is LR1 LR parsing approach. It is not amenable for writing hand-coded parsers. It's not amenable. So usually, if you want to write a hand-coded parser, you want to take the top-down approach. But LR1 parsing, but parser generators such as Bison, they use bottom-up parsing approach because it is powerful, and anyway the construction of the parsing table is automatic. It is algorithmic. You don't need to worry about manually keeping track of all the parsing table and actions, so on and so forth. Great. So now let's see, let's look at this grammar. We have seen this grammar multiple times before. to understand ambiguity, you know that the grammar you have, it's an ambiguous grammar. So that means the reason is it doesn't capture the associativity uh, properties required for parsing. That is whether, like for example, the addition operation should be left associative or right associative. The same is the case with multiplication operation. And then there is no precedence between addition and multiplication that is being captured here. So if you see this LR1 automaton associated with this grammar, this is a partial LR1 automaton. It is not a full LR1 automaton. And then we can understand few things here. Let's say when we are in state 3, and if the next input symbol is plus, so let's say we are in state 3, and if the next input symbol is plus, and what happens is if you take a look at this LR1 item, what this LR1 item tells is shift the plus symbol onto the stack and go to some other state. So this LR1 automaton is not complete, but if you complete, then we will know that after that it is possible for us to shift plus onto the stack and go to some state. But on the contrary, if you pay attention to this LR1 item, what this LR1 item tells is, it tells that apply a reduction operation. So there is a conflict between this LR1 item and this LR1 item. So this LR1 item says shift the plus symbol, and this LR1 item says, apply a reduction operation. The next look ahead symbol is plus, and this one says, no, shift the plus symbol onto the stack, and this one says apply a reduction operation. And this is what is called as shift reduce conflict. And when there is a shift reduce conflict, then that means the grammar is not an LR1 grammar. It is not LR1 parsable, because there are two possible actions. There are two possible actions to take, and so that means there is an ambiguity, and the grammar is not LR1 parsable. So usually when you use Bison and try to construct a parser for your programming language, you do get some shift reduce conflicts. And the way to resolve some of these shift reduce conflicts can be resolved. Like for example, in this particular case, if you would like the addition operation to be left associative, then you tell the parser to perform a reduce action. But on the contrary, if you would like your addition operator to be right associative, then you tell the parser to shift and move forward. So you want to do a reduce operation, so use reduce. So lean towards reduce if you want plus to be left associative. I am using LA for short, and then lean towards the shift action if you want your addition operator to be right associative. RE stands for right associative, LA stands for left associative. And then there is one more problem also. Let's see if it is here. Yeah. So let's say we are in state 3 and the next input symbol is star. So again, we are in state 3 and the next input symbol is star. And if the next input symbol is star, what this LR1 item says is, it tells a shift action, shift star into the stack. Shift star into the stack. This is, but then if you look at this LR1 item, this says shift. Okay, but this LR1 item, it says apply a reduce operation, and it wants to apply a reduce operation using the substitution rule, E goes to E plus E. So again, there is a shift reduce conflict here. So because of this shift reduce conflict, again, the grammar turns out to be not LR1 parsable. But so what we can do is, if you would like to give higher precedence to the star operation, if you would like to give higher precedence to the star operation, then we want to lean towards the shift. Like for example, the input is something like a plus a star a. Then if you want to give higher precedence to multiplication operation, then this is the kind of tree that we are expecting. So in which case we don't want to apply a reduction, because if we apply a reduction, then then a plus a, then the kind of parse tree that gets generated will be something like this. So we don't want this to happen. So we can tell the parser star has higher precedence, so shift, perform the shift action as against the reduce action. Similarly, but on the contrary, if you would like to give addition more precedence than multiplication, then you can tell the parser to perform a reduction operation, that is lean towards this as against a shift operation. In which case you will end up getting parse trees corresponding to this. You will get a AST parse tree and an AST which looks like this. So like this, most of the ambiguities that we face in expressions, etc., so they can be handled by telling the parser to lean towards one shift action versus another versus reduce action. So you do get shift reduce conflicts. You tell the parser, so please do this, stick to this shift action as against reduce action, or the other way around, depending upon your language precedence rules. Let's see. So here again, if you take this example, if you take this example, this is the if then else ambiguity that we have. In this if then else, so this is again a partial LR1 automaton for this grammar, and this grammar captures the if then else ambiguity. That is, the else should match to which if part. So in order to understand this ambiguity, if you go and look at state 7, then so you can see if the next, again here, you can see if the next input symbol is E, then else statement, then if E stands for else, this LR1 item says apply a reduction, and this LR1 item says apply a shift operation. So this is shift and this is reduce. So again, we can tell the parser to lean towards shift or reduce depending upon the kind of if then else semantics that we would like. All right. Are you with me here? Do you have any questions? If you have any questions, you can ask me now. So we don't have an example of, there is another kind of problem which is called as a reduce conflict. Reduce conflicts are much serious. So if in a, let's say in state I3, for the sake of, so if we have two LR1 items like this, the next look ahead symbol is A, and A goes to alpha 1 dot this, or A goes to alpha 2 dot A. So if the next symbol is A, then there is a problem. We don't know whether to apply the first reduction, A goes to alpha 1 or A goes to alpha 2. Or we may even have something like B goes to alpha 1 dot A also. So when the next input symbol is A, and we have to, then there are competing reduction operations, then we get what is called as a reduce conflict. So again, when there is a reduce conflict, then we say that the grammar is not LR1 parsable. So if you want to know whether a grammar is LR1 parsable or not, you start with the grammar, you construct an LR1 automaton, you construct the LR1 table, and then you check whether there are any shift-reduce conflicts or reduce-reduce conflicts. And if there are no shift-reduce or reduce-reduce conflicts, then the grammar is LR1 parsable. And if a grammar is ambiguous to start with, so you don't need to do the whole construction process, you are bound to get shift-reduce or reduce-reduce conflicts. And depending upon the grammar, you can tell the parser to either lean towards a shift action or a reduce action, or lean towards one particular reduction operation versus another particular reduction operation, and try to resolve the ambiguity. It is not possible all the time, but in some cases, it is possible to deal with the ambiguity in that particular fashion. And if you are not able to take care of the ambiguity in this particular fashion, then you have to go back to the context-free grammar and rewrite the grammar so that that particular trouble-causing ambiguity is eliminated. So now let's go to the last part of today's lecture, which is on LALR1 grammars. So if you consider this LR1 parsers, the big problem for them is the size of the parsing table will be very large. The number of states in the LR1 automaton, it will be really big. Since the number of states in LR1 automaton is large, then the associated parsing table, LR1 parsing table, will also be large. I would say this is not really a big deal for modern computing systems where we have enough RAM available. But when the theory of parsing was developed, let's say 30 years back, the available memory in systems is like 640 MB. It's not even 640 KB, 1 MB, 2 MB like that. So it's not even 1 GB. So way back, 30 years back, this is 2020. If you see 1990, 1980, 1970s, when the theory of parsing was developed, the size of the memory, it is very critical, because the first systems, the PCs that are coming, that are designed at that time, so their memory used to be like 640 KB, 1 MB, 2 MB like that. During those times, the memory is really a constraint. So because of that, you don't want parsing tables to occupy a lot of the computer's memory. But these days, you have everyone has at least 4 GB memory, and the new norm is 8 GB. And if you go to production systems, it will be maybe 16 GB, 32 GB also like that. So memory is not really such a constraint. But nevertheless, let's take a look at these LALR1 grammars, which are designed to reduce the number of states in the LR1 automaton. So in the LALR1 approach, so you take two states, and if the kernel of those two states is the same, like for example, this is the kernel of one state, and this is the kernel of another state. So if you look at these two kernels, and if you ignore these, the second, the look ahead symbol on the second coordinate, then you will see here you have S goes to dot ID, and here is S goes to E dot. And the same here, E dot. So now it's the same. So this is this, both are the same. So when the first coordinates, if you project the first coordinates, and if the projection turns out to be the same, then we say that these two states are equivalent, and we merge them. So we take these two states and we merge them, and this is what we get. This is the resulting state that we get. A shorthand for this, a shorthand for representing this is as follows. Let me. So we also write it as S goes to dot ID plus or dollar. This is a shorthand representation for it. So the idea is through this table compaction process, we can reduce the number of states in the LR1 automate. And the Bison parser generator, it can generate both the LR1 parsers and the LALR1 parsers. The parsing algorithm remains the same. The only thing that changes is the way we construct this automaton changes a bit. So now let's take a look at this automaton, this LR1 automaton for the example grammar that we have here. And if you see here, so there is a state 4 and state 7. If you project their the first coordinates of the LR1 items, they turn out to be the same. So here there is only one LR1 item, and that is, and if you look at the first coordinate, it is C goes to D dot. Similarly, this is C goes to D dot. So both these are the same. So we say states 4 and 7 are equivalent. Similarly, we say state 3 and state 6 are equivalent. Let me use a different color maybe. Yeah. So state 3 and state 6, they have the same color, they are the same. And then similarly, state 8 and green color, this is green, this is green. So these are all equivalents. So these are equivalent states. So what we would like to do is we want to merge these states. But one thing, there is one problem that you may want to worry about is, let's say there is a state I and there is a state J, and you realize that they are equivalent to each other, so you want to merge them. So after merging, let's say there is a symbol X, there is a symbol A, and on looking at symbol A, this goes to I prime. This is in the original LR1 automaton. In the original LR1 automaton, this is how it is like this. Like for example, I is 6. On looking at this capital C or the non-terminal C, it goes to state 9. And similarly, if you see J, it is equivalent to state 3. On looking at C, it goes to state 8. Let me write it here. This is what I mean. State 9, and this is 3 on non-terminal symbol. This is 8. So when we merge these two states, we can get into a problem. Let's say we merged them, and IJ is the merged state. And on looking at A, then in the merged LR1 automaton, on looking at A, there is a problem. So whether we should be going to, there are two possibilities, whether we should be going to I prime or whether we should be going to J prime. Because in the original LR1 automaton, when we are in state I and when we see A, we go to state I prime. And when we are in state J and when we see J, when we see that the symbol A, we go to J prime. So there are two possibilities here. So how do we reconcile? It so turns out this is not a problem because these two also turns out to be equivalent to each other. So we will end up merging both of them. So we will end up merging both these. And you can see here that, if 6 and 3 are equivalent to each other and 9 and 8 are also equivalent to each other. So when we merge 6 and 3 and we get the state 63, then it's really not a problem because 9 and 8 are also anyway going to get merged. And this is the claim that I would like you to prove, that if state I is LALR1 equivalent to state J, then GO2 of I comma AX is LALR1 equivalent to GO2 of J comma X. So this is a claim. This is the homework problem that I am going to release for today. So you have to prove this claim. So now let's see how this is the LR1 parsing table for the original grammar based on, based for this LR1 automaton. For this LR1 automaton, this is the LR1 parsing table. And what happens is you can see what is state 6 and 3 are equivalent. So state 6 and 3 are equivalent. So what we do is we merge these two states, two rows together. And what happens is in the new LR1 parsing table associated with state 63, you will get that when you are in state 63, and if you see the symbol C, what you will do is you shift and go to state 63. And when you see D, you shift and go to state 47 because 4 and 7 you are going to get merged. And in the go to part, when you see the non-terminal symbol C, you go to state 89 because 8 and 9 are going to be merged. They are equivalent to each other. Okay, and that's what you will see here. That's exactly what you are seeing here. So this is the merged, this is the LALR1 parsing table after applying the compaction process. So, and we say that a grammar is said to be LALR1 parsable if after doing this compaction process or a merging of states, there are no shift-reduce conflicts or reduce-reduce conflicts. And there is an important question, again, I will give this as a homework problem for you, is when a LALR1 automaton is constructed from LR1 automaton, we can only expect to see reduce conflicts, but not shift-reduce conflicts. That is, in the original LR1 automaton, there are no reduce conflicts, there are no shift-reduce conflicts. And then we applied a compaction process. After applying a compaction process, it's not necessarily the case that the compaction process will go nicely, because after compaction, there can be shift-reduce conflicts or reduce conflicts, which makes the grammar not LALR1 parsable. If there are no shift-reduce or reduce conflicts after the compaction process, then the grammar is LALR1 parsable, and that is the best thing that can happen to us. Because we didn't lose out on any power, we are still able to parse the grammar, but the number of states has reduced. But it is possible that after compaction, there can be reduce or shift-reduce conflicts. And the claim here is it is possible to have reduce conflicts, but not shift-reduce conflicts. Why is it the case? This is another homework problem. So because of this, if you see LALR1 is a strict subset of LR1, because there are grammars for which are LR1 parsable, but not LALR1 parsable, because after compaction process, new conflicts can arise. So with this, I conclude today's lecture. We will conclude today's lecture on LR1 parsing. In the next lecture also, we will see a little bit more about LR1 parsing, because we would like to see how we can enhance an LR1 parser so that as a byproduct of the parsing process, an abstract syntax tree is constructed. That is a very important idea that we will see in the next class. And that is all for today. So today I will release this week's homework. So there will be 3 parts. There will be, the first part will be, I'll give a context-free grammar, some grammar G, and I'll ask you to construct an LR1 parsing table for it. This will be one problem. And the second problem is this question. So the second problem is actually this one. So I want you to prove this claim that which is related to equivalence of states in LALR1 automaton. And the third problem is related to this. And when you solve these 3 problems, then your understanding of LR1 parsers will be complete. So I really want you to use this homework as an opportunity to complete your understanding, on bottom-up parsers. Because unless you think by yourselves, these ideas will not be clear. So please take this homework as a learning opportunity. I will release this homework by today. And if you have any questions now, you can ask me.